Now that we've talked about covariance, we're also going to talk about a related topic, correlation. Correlation is based on a similar idea to covariance in that both of these quantities give us information about the relationship that two different variables have on each other. However, at the same time, correlation is also quite different. So in this video, we're going to dig deep into the concept of correlation. How exactly is it different from covariance? We're also going to talk about some of the details of correlation. Do two dependent variables necessarily need to have a non-zero correlation? Or is it possible for there to be specific cases when two dependent variables could have a zero correlation? Once we do that, we're going to go into more detail and we're going to approach a couple of examples where we calculate correlation. And hopefully these will make it clear about the differences between correlation and covariance. Hi, in this video, we're going to talk about the concept of correlation. We're going to talk about how it's different from covariance, how it's similar to covariance, what kind of additional information it gives us. And we're also going to dive into some examples related to the calculation of correlation. So let's go into it. As we mentioned in the previous video, covariance gives us some information about the relationship between two variables, right? It gives us information about the direction of the relationship, but no information really about the strength of the relationship. When I say it gives us information about direction, what that means is a positive covariance means that both of the variables increase and decrease together. And a negative covariance means that one variable increases as the other decreases. However, covariance is not normalized, as we might remember, which means it actually does not give us any information about the strength of a relationship between two variables. Since covariance is not normalized, it can have pretty much any value, and the value depends a lot on the scale of the two variables in question. But on the other hand, correlation, the concept that we're covering in this video, gives us information about the strength of the relationship and also information about the direction. So the direction is what covariance gives us, but correlation gives us additional information which indicates the strength of the relationship. And the reason for this is because correlation, the correlation coefficient, as we describe it, is a normalized quantity. It takes on values between -1 and +1 inclusive. And a negative correlation coefficient implies that, obviously similar to covariance, both the variables move in opposite directions. A positive coefficient implies that both variables move in the same direction, that is, they either increase together or they decrease together. And the other thing about the correlation coefficient is if it is 1 or -1, that implies a perfect linear relationship between two variables. We've thrown around this term strength of relationship a lot. And so maybe it might be worth spending a little bit of time on it and talking about exactly what that means. So let's take maybe 3 different examples. I'm going to do this in black. So we have, we have 3 different examples. I'm going to leave the space on the top right in case it's likely to get covered. So we have x and y, and x and y. So now let's take 3 different kind of data sets which have x and y. So our first one looks something like this. We have values for x and y. We have a relationship between these two variables, which quite clearly seems to be increasing, right? So as the value of x increases, the value of y increases too. And it is possible to draw a kind of best fitting line that kind of goes something like that for this data set. Now we have, say, let's call this example 1. Now we have example 2, which looks something a little bit like this. So we have a similar linear relationship between the two variables. And let's say it's something like this. So we still have it so that x, an increase in x also kind of portends an increase in y. And we can draw a very similar, oops, that was destructive. Let's kind of patch that up a bit. So we have that, and we have a bunch of points down here. Yep, perfect. Okay, so now we're gonna go ahead and draw this line that kind of explains the data pretty well. It's gonna look very similar to what it does in case one. So it's gonna be kind of a straight line with a very similar slope in this case, and starting at x is equal to 0, y is equal to 0. And now for our third case, we're gonna get a set of points which looks like this, right? So they all actually pretty much lie on the exact same line, and it's possible to draw a line through pretty much all of them. It's not perfect. You can still see some of the points, I hope, but the idea I'm trying to convey is that the line kind of fits all of the points that are on it. So when we talk about strength of a relationship, you can think of it almost as like predictability. So with what certainty are we able to predict an increase in y, given that we know an increase in x? You could think of it kind of broadly in those terms. I don't know if that's exactly the right way to put it. You could also think of it in terms of like how well it fits this given line. So if we were to compare the correlation coefficients of cases 1, 2, and 3, it's pretty evident looking at this that we would see 3 have a higher correlation coefficient than 2, which in turn has a higher correlation coefficient than 1. And in fact, since pretty much all the points in case 3 lie on the line, we can actually say that the correlation coefficient in case 3 is almost equal to 1. Because it's a normalized quantity, right? And 1 indicates a positive relationship and also a super, super strong fit. So we can be pretty sure that in case 3, our correlation coefficient is either 1 or very close to 1, depending on how many points are slightly off the line. So that's kind of what we're talking about when we talk about strength of relationship. So I just wanted to address that because I have been using that term a lot and I wanted to kind of clarify what it meant. So this is kind of what we were talking about in the previous slide about a positive correlation, a negative correlation, and no correlation. So in terms of case 1 over here, we can draw a line that explains the data very well, which goes something like that, right? So it's a line with a positive slope. Y increases as x increases, so that is a positive correlation. In case 2, we see the opposite. We see a line, like a linear relationship that is in the negative direction. So as x increases, we see that y decreases. And in case 3, we actually don't see any kind of like linear relationship, any kind of reasonable linear relationship. We could potentially draw a line that looks like this, but that does not seem to adequately represent the data. And frankly, we can't even say it's any different from a line that goes this way, right? So it could be absolutely anything. In this case, it's pretty clear that y and x have no correlation. They have a correlation coefficient very close to 0. And what that means in this case is we're not going to be able to decide whether it's a positive or a negative correlation. There's no clear relationship between the variables x and y in this case. So as with covariance, there's also a formula for correlation coefficient. And there's a term over here, which is this, which you could think of basically at a high level as like basically the standard deviation of x and the standard deviation of y. But what's happening in this case is where this is a term that normalizes our quantity over here. So on top in our numerator, we have the quantity sigma xi minus mu x, sigma yi minus mu y. And then this is divided by the square root of sigma xi minus mu x squared, yi minus mu y squared. So this is how we can go about computing our correlation coefficient. This quantity will be between -1 and +1. We're not going to cover the kind of proof of that over here, but that's just something to remember. So overall, this quantity is going to be normalized between -1 and 1. It's going to be indicative of the strength of the relationship between the two variables. And a good question that comes out of this is, do correlation and dependence mean the same thing? Like if two variables are correlated, does that mean that they're dependent on each other? And I think the inverse is more interesting, where if two variables have a correlation coefficient of 0, does that necessarily mean that they're independent? So maybe that's something to look at.